We're looking back at transformations today and the idea of transformations specifically that produce similar but not congruent figures. We've talked about this before, but we're going to talk about it in a more focused way now that we're talking about similar versus congruent. So, is there a similarity transformation that maps triangle ABC onto triangle RST? If so, identify the similarity transformation. Use words from the list below to complete the sentences and answer the question. So first of all, triangle ABC and triangle RST appear to be similar figures. And by that, remember, we mean that they are the same shape, but they could be different sizes. And in this case, they are different sizes. So they have the same angles, but different side lengths. Two figures are similar if and only if there is a similarity transformation. I'm going to write that down here because it won't fit on the line for me. Similarity transformation that maps one figure onto another. So a series of transformations, including a dilation, that would move this triangle onto this triangle. A similarity transformation is a composition. Remember, a composition is multiple different transformations that are done in a sequence of rigid motions and dilations. And just as a quick reminder, we talked mostly about rigid transformations when we did transformations last semester. So that includes over here reflections, translations, and rotations. Those are all rigid transformations because they don't change the size or the shape of the shape that we're transforming. Dilations are the ones that are similar transformations because they change the size but not the shape. So it'll be proportional, it'll still be the same shape, but it'll be bigger or smaller than it was before. So back over here, since triangle RST is an enlargement of triangle ABC, so this is bigger than this, we're going to start by first performing a dilation or a size change with a center at the origin and a scale factor of 2. So meaning triangle RST is going to be twice as big as ABC. And we can see the corresponding sides. This is 2, this is 4, this is 1, this is 2. So this is twice as big as this is. So we go ahead and do a dilation. We make it twice as big. Then we see what else we could do to move this so that it's in this position. Since the resulting image and triangle RST have opposite orientations, so they're flipped around from each other, we're going to perform a reflection across the x-axis, which is the line of reflection. Line of reflection. So we flip it across the x-axis, it gets flipped upside down to right here. And then finally, we apply a translation that slides the second image 7 units to the left to map it over RST. So this is a dilation followed by a reflection followed by a translation to transform this smaller triangle into this larger triangle. These are similar shapes, but not congruent. And again on the back here, if you fold this over for when you're going to glue it in, you'll have this handy transformations cheat sheet to help you remember things about the rules of how we do reflections, how we do rotations. Those are the ones that are tricky in particular. And then some basics about applying scale factors for dilations and coordinate changes for translations. Now let's take a look at how we prove triangles similar to each other. And I'm going to cut this down so that it'll fit better inside the notebook. And you can cut it down like this as well when we are done writing so that it fits better inside your notebook. So a 2-foot vertical post casts a 16-inch shadow at the same time a nearby cell phone tower casts a 120-foot shadow. How tall is the cell phone tower? So first, when we have a situation like this, it's really helpful to draw a sketch of the situation that's described in the problem. So I'm going to draw first a 2-foot vertical post. So this post is 2 feet tall, and the sun is shining down, causing it to cast a shadow onto the ground, like this. And that shadow is 16 inches long. At the same time, there is a post that we don't know how tall it is. It's X feet tall. So we don't know how tall this is, but it's definitely not going to be to scale. So we won't worry about making sure that these are proportional the way they should be. because this is just a sketch for our reference. And then, of course, this one's also casting a shadow down onto the ground. And it's going to be at the same angle because the sun's in the same spot in the sky. And it is casting a shadow that is 120 feet long. So we label this with the information that we know, and then we can go from there. So this is X feet tall, and this is all the things that we know about it so far. Now, because we've connected the top of the figure to the end of the shadow in each case, what kind of figure have we formed here? We've formed a pair of right triangles. And we're told, right, that this is a vertical post, so it's sticking straight up from the ground is horizontal, so that makes these right angles, which is why these are right triangles. So how are these polygons related to each other? They are similar. So they are the same angles, but they are different sizes, which means that they're going to be proportional, and that's how I'm going to solve this missing piece. Which parts are corresponding? The heights of objects, which are respectively 2 feet and X feet tall. And then the lengths of the shadows, which are respectively 16 inches and 120 feet long. In our diagram, which corresponding parts have different units? The shadows, one of the shadows is in inches and one is in feet. So those are in different units. Shadows are in both inches and in feet. So what do we need to do so that the corresponding parts have the same units? We need to convert feet to inches, because if we don't do that, we're going to be dealing with a really ugly decimal or trying to multiply using a mixed number. And so with converting feet to inches, we'll be dealing with whole numbers only. So 120 feet times 12 inches per foot is 1,440 inches. And 2 feet times 12 inches per foot is equal to 24 inches. So now all three of these things are in inches. So now we're going to update our diagram. We've got a right triangle that is 24 inches tall and has a 16-inch base. And then we've got a right triangle that is 14, or that is X inches tall and has a 1,440-inch base. And now we can write a proportion. So we're going to put 24 over 16 and X over 1,440. Again, there's several ways to set up a proportion. As long as you're using the same rule of corresponding parts, you'll end up with the right answer. So if we cross multiply, 24 times 1440 is 34,560, and 16 times x is 16x. Then I would just divide both sides by 16, and I get that x equals 2,160. So now I'm going to convert that into feet. 2,160 inches divided by 12 equals 180 feet.